We begin at the Salto Bayo Falls in Brazil, where this fellow took the express elevator to the basement via kayak. Pedro Olivia rowed his boat a record 127 feet to the bottom of the falls and amazingly survived without a scratch. The drop took exactly 3 seconds. It breaks the old record by about 20 feet, and while it looks like they might have just chucked a dummy over the falls, like in the movie The Fugitive, the stuntman and his friend appeared on the Today Show this morning to verify the story. Mr. Olivier then kayaked off the Prometheus statue into the ice skating rink at Rockefeller Center. More stunt activity, this kind unintentional or non-intentional. That's Neville Township, Pennsylvania. Neville's not a good driver. All right, the truck driver, whoever it is, needs to work on the cornering. Apparently, he was packing cardboard, which will sail on you if you go a little too fast on the edge. The accident happened just outside a chemical plant, so this could have been anything but funny. As it was, the driver was just slapped with a speeding ticket and cited for overturning his vehicle. He was not injured.
That's a funny one.
First, a lot of great birthdays on March 26th. Actors Sterling Hayden and Alan Arkin and Leonard Nimoy.
So, yeah, I was going around the corner a bit too fast on that. So, actually, that's interesting. I didn't think that this one who survived. So, this was in 1989. I know because I was very close to Niagara Falls at the time. Jesse Sharp decided to kayak off Niagara Falls, which look about the same as the ones that we've just seen. But he disappeared without trace. I guess there's a little story here that says he went off not wearing a helmet, not wearing a life jacket because he thought it would hurt his chances of floating up to the surface again, and booked himself a meal at a restaurant downstream for the same night. I guess he was expecting to survive. So anyway, all by way of saying that if you think your lives suck this morning, this guy's was worse off. So anyway. So any last thoughts before this evening? I apologize that today will be kind of a long day for you, but I think there's no way around that. I guess we all look at, I know that when I make presentations, you all think, oh geez, they're going to be criticizing me in a presentation, and exams are perhaps just the same, but really the positive thought would be to say, well, I get to show people what I know today. And so same for presentation, same for an exam. So I know it's sometimes difficult to think in those terms when you've got the weight of the world on your shoulders, but go in there and just show what you do understand. Any last questions before we roll with today? No? Okay, so yeah. All right. I'm going to look at this as well. This is quite... This is from a year ago, as you can see. Actually, some of us were in Iceland this summer. I don't know if this was still erupting, and it certainly wasn't anywhere near where we were. But this is the difficult to pronounce Bardarbunga volcano. Sounds like a Silvia Berlusconi joke, doesn't it? Bunga Bunga. And this is a volcano that was erupting in the summer. It didn't turn out to be as devastating as the other one that's impossible to pronounce, eruption or whatever it is, which was the one that was erupting maybe underneath a glacier in 2011, I think, and shut down all of the airspace to Europe. Most of the routes from the east coast and the west coast of the U.S. to Western Europe take a great circle route, which goes quite close to Iceland. It goes the shortest distance between 2 points on a sphere is a great circle, and that great circle passes pretty close to Iceland. And so this never turned into the huge ash discharge that was the problem with Eskifjord, which I think over maybe for 1 or 2 or 3 weeks shut down airspace between Europe and the US, primarily because you don't want to be flying into an ash cloud because it's not very good for the engines. It strips the engines. I think it doesn't do much more than that, but the question is how much ash is too much ash. And there certainly has been one. I don't know whether we mentioned in this class, there's a KLM 747 that was flying to Anchorage and went through a dust cloud, I think maybe from Redoubt, and all of a sudden the cockpit goes dark, all 4 engines flare out, and all of a sudden, that's not really where you want to be in a plane, where you can only hear the wind around you, I don't think. And they ultimately did get them restarted and landed safely, but a hazard nonetheless. And so, also, if you go to Asia, all the Pacific routes go down, you go over the pole. If you go to Beijing or go to Tokyo, you go over the pole and then you come down across the Kamchatka Peninsula, which is volcanic. And so the Ring of Fire, you basically travel the Ring of Fire by plane. And so there's one of the hazards is, of course, knowing when these volcanoes, which are obviously in the wild, erupt, and as a result of that eruption, create this hazard for aviation. So anyway, so all by way of saying, when we're talking about fluid dynamics, we now have enough information to be able to do something about that. And so we can look at the mechanisms by which eruptions occur. We can do a very simple calculation. And the simple calculation I was just going to do, just for the hell of it, was to... So one question would be, where are we? We're 5. Still talking about fluid dynamics, still talking about Bernoulli. And so you have this system that looks something like this, where you have a volcano sitting on top of the crust. The crust may be something like 30 kilometers thick. And so the question is, or one question could be, what velocity? And so we can use Bernoulli simply to do that, so long as we constrain it. And we do exactly what we've done in the past, and that is that we write Bernoulli at 2 points. We write out the 6 terms. We take this tack of always writing from upstream to downstream. As a matter of course, we don't need to do it yet, but we will do in the future. And all we need to do is figure out exactly what the component terms are. And so we've said that we need to know 5 out of 6 of them to solve for the 6th. And I suppose the 6th is this one here. So the question is, do we know what those other terms are? So we could make a guess, I suppose, that the fact that coming out, it's atmospheric. We know that if we take the datum as z equals 0, I guess you do get everything on there, whoops, then this is 0. I suppose this would be 30 times 10 to the 3. What other tricks can we use? Well, we talked about the code in these questions. Large reservoir. So in other words, if this big reservoir is so large that depleting a certain small amount to go through this fissure to come out of this is relatively small, then the velocity in this you can take as being 0, just by not say being at the entry to this conduit, but by say being here. And so by being here, you could imagine all the stuff that goes up here, but this is relatively unaffected. And so if that's the case, then all of a sudden we can assume this is 0. The large tank assumption. And so if we do that, we now have velocity as a function of fluid pressure, and we have to figure out what the fluid pressure is. And so you can probably get a pretty good estimate of fluid pressure just by doing P1 equals rho g h. The density of rock is something of the order of 2,700 kilograms per meter cubed. The mechanism by which volcanoes erupt is that you heat up rocks, they're molten, they have gas in them. Because they have gas in them, that gas actually makes the density less than the density of the rock that surrounds them. And so the density of the fluid at 1 is less than this, typically, because it has gas in it. And I'm going to choose a number which is 2650. It's probably too small. So that's the density of the liquid. The density of the solid, which is resting on this, is 2700. And so if you look at this, then this now is the pressure 1. So pressure 1 is equal to 2700 times, I'm going to call it 10 meters per second squared, times 30 times 10 to the 3. I don't know what that number is, but I guess we would calculate it out. And so we can just rearrange what's left, and we'll end up with V2 is equal to 2 times gravity times pressure 1 divided by rho fluid G square root, I think, which is equal to 2 times 2700 times 10 times 30. Well, it's a lot of numbers, isn't it? 10 to the 3 divided by this other density. This is the density of the fluid. And I suppose I could do that calculation. Did I do that calculation? I did that calculation if this is equal to 2600. And if that's the case, then V2 actually comes out to be equal to 144 meters a second, which is preposterous, of course, which is about 300 miles an hour. And it's conditioned by the difference. So in other words, if you take this number as being 2600, that's what you end up getting for V2. And that's much too fast. But it's conditioned by the magnitude that you choose for this. But the bottom line is that if you know or estimate the magnitudes of the pressure here, and if you know the density of the fluid that's driving, given the mechanism that's making it work, the mechanism is that you have a weight by the supernatant crust that sits on top of this. You have a fluid which is buoyant relative to that, and this buoyant fluid is rising up through this. Instead of being buoyant and calculating it as a buoyant force, Bernoulli accounts for that in some way because it's really balancing forces. It accounts for the fact that this magnitude is less than the column. So in other words, you have a larger pressure here than the pressure here, and therefore this stuff gets forced out, squeezed out like toothpaste. And so if we wanted to do that, we could do that using Bernoulli. So anyway, so just the basic calculation that we are going to want to do in these calculations. All right. So if we get back to talk, so all I plan to do today is talk about some examples. We've done one of them, I guess, already, an impromptu one. The examples rely mainly on our understanding Bernoulli, which we've already used, so we know we don't care what these losses are yet, and we don't care what this pump head is yet, and therefore it doesn't matter whether we write it upstream and downstream, because we don't have to worry about these. We know that the equation of a free jet is just this. We did that last time. And we'll do an example today to constrain it, but we said that if we know only 4 out of 5 of our constants in Bernoulli's equation, then we have to constrain it in some way. And one way we can do that is to write the upstream and downstream velocities as linked to each other, in which case, if we wanted to, we could now write very straightforwardly V1 is equal to A2 over A1 V2. And we could write this V1 as a function of V2. And so now, in this expression, instead of having 6 unknowns, we only have 5, because we've defined it in terms of V2. And so let's just do some examples related to that. Okay. So they're all contrived examples, but they're interesting in their own right, I guess. And so I'll talk not in terms of doing the calculations per se, but in terms of the philosophy of how we might want to approach these. And so this is a big tank that has a hose coming out of the bottom of it. And I suppose you could ask a question of what angle do you have to apply to that hose to get it to either go the highest or the furthest. Highest, I guess, on this would be the value of h, which I think is really what you're being asked here. But you could also ask how far you'd have, the angle you'd have to put it at so it goes the furthest. And so as a thought exercise, I suppose, we could do the two simplest arrangements of that. One simple arrangement would be to have this hose come out of here and to have the hose go up to here. And so if we did that, if we have point 1 here and we had point 2 here, we know that we can write Bernoulli's equation between those. I always write it in this form just because it's easiest for my simple mind. And start figuring out what the terms are. And so the first issue is that this is a big tank. If it's a big tank, then compared to squeezing a little bit of fluid out of here, the level of this tank is not going to go down very quickly. And so the big tank approximation allows you to basically put this velocity equal to 0. We know that this sits on the top, it's atmospheric. If we take atmospheric as 0 gauge pressure, which it has to be, right, then this is 0. If this is also at the same elevation, and it's also, well, actually, irrespective of whether it's the same elevation or not, if it's atmospheric pressure, then this is also equal to 0. We don't know what this second velocity is. We'd like to know it. But we do know the elevation of the point 1. If we take this as z equals 0, which is perhaps easiest, then this is definitely equal to 0. Sorry, it's not the case, is it? This is definitely equal to uppercase H. And so we could do two things. We could choose this to equal h and solve for velocity. And since h is equal to h, this has to be 0 by definition, right? And so if we have the tube, the hoses come up to this point, it would be exactly the same way that if you take a tube. What's the easiest way to find a level spot between 2 points? Is if you take a 10-foot piece of Tygon tubing, you fill it with water, and you just balance it so the water level here is exactly the same as water level here. It's by far the easiest way to transfer the same elevation to 2 points. It has to be correct, right? As you go from this fluid in this simply connected tube, the fluid pressures have to be the same at those 2 points. It's atmospheric, have to be the same elevation. So this is basically saying that if this elevation here is equal to h, then the velocity is equal to v2 squared. If it's not equal to h, if for instance it's equal to this point here, so in other words, if you cut the tube off at this point here, then this elevation here would be equal to h minus c2. And so, in other words, when you rearrange this expression here, you'd end up with this. And of course, this is the same as V2 is equal to this, which we have seen before. And so it actually works as a free jet, what we've called a free jet. Remember the free jet we talked about before was the hole in the bottom of a bucket. Free jet was going downwards. it actually doesn't matter if the hole was in actually the side of the bucket and it was squirting out horizontally. It'd be exactly the same expression, as indeed you have here going upwards, the opposite. And so this is a relatively important and interesting standard result that we'll use. Okay. So those are the two kind of end member conditions that are shown here. So if you have your tube that goes up here, it would only flow, and the velocity at this point you could imagine would be equal to 0. The maximum height that it would go up would be equal to the height of the water in here. Kind of makes sense. If you truncate the tube below that, then the magnitude of the velocity coming out of here, this would be v2, is going to be this, which is just equal to the head of water that's above it, h minus z2 in this particular case. Okay. So that's the big picture. What you're being asked here is to calculate what is the maximum height that this would go to. And so clearly if you arrange this tube so it's horizontally, then the maximum height that it would go up to would be 0, because you'd be shooting horizontally. It would come out at some velocity. What's the velocity it would come out at? Yeah, square root of 2gh, right? Be the full length of this. So it'd come out of this thing at the velocity of square root 2gh, uppercase h. If you have it going vertically, then we've just shown that the height, the maximum height it can go to. If you cut this off slightly short of this, you see it bubbling out over the top at some small velocity, because this magnitude of z would be shrinking around to 0. Did I do this right in this case? H minus c. No, yeah, okay. So why didn't you tell me this is wrong, right? So this isn't 1, right? This isn't h. This has to be 0. And so this, instead of being, this is h minus, yes, h minus c2. Has to be this, right? So the velocity is the difference between these two as it comes up here. So as it comes up to the top, then it's going to asymptote to 0. So if you cut it slightly below the top, where z2 is not quite equal to h, then all of a sudden there's a very small number here, and it means it's just bubbling over the top. And so to solve this, I guess, the question is, how do we calculate the magnitude of this particular height? And so the observation is this. What we could do is we can now write Bernoulli between point 1 and point 2. If we did that, what do we know about this? We know this elevation, we know this pressure, and we know this velocity. So if we know those, this pressure is 1 is equal to 0. The velocity 1 is also equal to 0, the big bucket assumption. And the elevation of that point is equal to h. So, oh no, that's right. I guess yeah, this is wrong, right? So what's? So yeah, okay. So this is what's wrong, right? This is here. This, yeah, I'm not doing a very good job for you today. This is h minus c. This is correct, of course, right? It's the difference. So this, the height is always h of point 1, which I guess we have here. And so the height of point 2 is always equal to z2, whatever that is. And so we're subtracting off plus z2 onto the left-hand side. So these are the requirements, if you like, for point 1. The requirements for point 2. So what's v2? v2 we don't know. The pressure at point 2 coming out into the atmosphere, right? So the same arguments that we've used before. The pressure acting perpendicular to this is atmospheric, and so since the pressures acting at points have to be the same, then P2 is equal to atmospheric also. And if we're doing our calculations in gauge pressure, it's equal to 0. And the other requirement is that it has some elevation, which in this case is equal to L. This is going to be equal to L times the sine of theta, which is this. And so if we look at these 2 points and we wrote Bernoulli between them, we have 3 values here. So we know all the 3 values upstream. We have 2 values downstream. And so we don't know what V2 is. So with this information that we have, we could certainly solve for V2. And this is exactly the expression here that solves for V2. And the only unknowns there are going to be this. So we don't know V2, but we know all the other components. So we have a value for V2. So how does that help us getting this height? So if we know what V2 is, then we could do it 2 different ways. The first way that they do here, this is just the solution out of the book. So the fluid that comes out of here comes out with some velocity V2. So we know that if I take, I don't have anything to throw, but if I'd have a battery to throw. You know that if I throw a battery over to the other side of the room, we won't worry about that, is that as it leaves my hand, if it doesn't have drag acting on it, Newton's law says that the body in motion keeps on in motion unless it's acted on by something else. And so the velocity comes out of my hand, if it's not acted on by wind drag, means it would carry on horizontally at that same velocity. And so you can use that here to be able to calculate the magnitude that the velocity, the horizontal velocity, component of velocity that comes out of here, has to be the same velocity that it goes through here at, and has to be the same horizontal velocity it has when it strikes the ground. And so that's the one thing that you can use here to be able to calculate this. So now, so from Bernoulli's equation, the only unknown that we've solved for is velocity 2, which is this. So we have velocity 2. This is a streamlined velocity. It's aligned along the jet, and it's this magnitude here. We know that the magnitude of the horizontal component of that, V2x, is going to equal to V2 cosine theta. Right? Just from this triangle here. This component here is going to be V2 cosine theta. And so we know that this is going to be equal to V3, right? By definition. And so now, if we write Bernoulli's equation between point 2 and point 3, which is this, I guess I won't move it up so you can't see it, which is this expression here, then we figure out exactly what we know. We don't know V3, but we know that that is equal to V2. We know it's equal to this, right? We know that V3 is equal to V2 cosine theta, and we know what V2 is. So in some respects, we know what this is. We know the pressure at 3. Pressure at 3 has to be 0, right? By definition. We know the elevation of 3. Well, that's actually what we want to find out, right? This is h. So we have this term which we don't know. We know the pressure, I guess actually working at, this is written between point 3 and point, we could do it with point 2 as well, I guess. But if you write it between 3 and 1, the pressure on the top of the tank is 0, the velocity, the big tank assumption is 0, and the elevation of that top surface is equal to h. And so the only thing that we don't know here is h. We know what V3 is as a function of all of these other terms, which we know. We know the height, we know the length, etc. And we can solve for the magnitude. Not so easy to solve for, but basically that's the complicated expression. Doesn't matter what the complicated expression is. The only trick, I guess, to doing this is to realize that fluid coming out of here. It has a streamline velocity v2. We can describe that streamline velocity into a horizontal component and a vertical component. We know the horizontal component, if the water is not acted on by something else to slow it down, which it isn't, it will continue horizontally at the same velocity. So the horizontal velocity at 2 has to be the same as the horizontal velocity at 3, which happens to be the streamline velocity. And the horizontal velocity at 4 would also be the same horizontal velocity that strikes the ground. So that's the way to do it. The other way to do it, which I think is not so, perhaps it's more straightforward. What's the other way to do it? That you can use Newton's law to solve. Where did my battery go? My prop. So the one thing that we could ascertain, well, figure out from this is that something moving with a velocity as it goes in this direction. So the same horizontal velocity, if it's not acting on, it keeps on going. The other observation is that if it goes upwards and reaches the top of its arc, then it's the same deal, right? It has gravity acting against it. So now what the other alternative way to do it would be to do this, to realize that as it comes out of here, it has this, this streamline velocity. The streamline velocity, you can make a horizontal velocity or a vertical velocity. So this would be v2z. And so you know the velocity that it comes out of here is equal to some, at this height here, is equal to v2z. And if you know the velocity it comes out with, you could use Newton's law to find out the height of the arc that it goes up to the top of. Just by using, by integrating this expression. So, what is it? You remember the expression, right? So what is it? That velocity 1 is equal to velocity 0 plus acceleration times time. This is just saying that the velocity you start with is equal to whatever it is coming out of here, plus an acceleration times time. This is change in elevation with time. And so you could write this out as dz is equal to v0 dt plus acceleration times time dt. Got a cramp here. And this just becomes, this is z0, z1. This is t0, t1, t0, t1. And you certainly know this expression, right? So this ends up being z1 minus z0. The distance traveled is equal to v0 t1 minus t2, the time taken, sorry, t0 minus t1, plus a half a t0 t1 squared minus t0 squared. This is backwards, right? This is, should be t1 minus t0. You've seen this. This is your normal dynamics equation. It just says the distance traveled is equal to v0 times time, since 0, plus a half at squared. This is gravity. And so if you know the velocity it starts with coming out of my hand, then you have to count until it becomes 0 velocity at the top of its arc, and that allows you to calculate exactly what z is as a function of that. So you can calculate z in this case would just be the height it would go. And so it's just a matter of dissecting it. So you can do it either way. So the realization is that the jet coming out of it comes out at some streamlined velocity, v2. You can think of that either as a horizontal velocity, which will always keep it as the same magnitude because there's nothing acting on it, and calculate exactly when the streamlined velocity at the top of the arc is equal to that same magnitude. Or you can take it as it comes out with some vertical velocity, which is the velocity it comes out of my hand, and you can calculate the height of the arc that it goes to before the velocity at the top of the arc becomes 0, and that height that it goes to is that same amount. And so it's just a matter of dissecting these expressions to do that. Up for another one? Well, again, a contrived question. We have two beads of water. They impinge on each other. One's being driven by an overpressure with an air cushion that's driving this flow. The other one is just due to basically a free jet, so atmospheric pressure on here that impinges on this. And the question is, what are the magnitudes of what's the height of this that it will give you? What is the height that this bucket is above the other one that gives you the conditions that these two jets meet and they exactly dissipate each other at the location where they meet. And so what we can do is we want to be able to figure out exactly what this is. And I suppose we also want to figure out exactly what the magnitude of the pressure at A is as well. And so what do we know about this? Well, this is a stagnation point, right, by definition. And so by definition, the velocity at A should equal 0. And also the velocity coming up should equal 0 as well. I guess both of these are VA. And so we can write Bernoulli's equation for these. So point number 2. Pressure has to be 0 because it's atmospheric. If it's a big tank, then the velocity is 0 because it's a big tank and not much stuff is coming out of it. And the elevation has to be, if we take this as the datum, z equals 0, then it's 20 feet plus an unknown value of head to get to this point here. So if we write Bernoulli between point number 2 and point A, which is this expression here, then this is atmospheric. This is a big tank. This Z2 is going to be equal to 20 plus H. Because this is stagnation, two cars coming down the highway, both going at 20 miles an hour, they hit each other. At the moment of impact, they each have 0 velocity, right? You can think of this as a water stream as just being a rejuvenation of cars hitting each other. So the velocity by definition has to be stagnation. So this is 0. We know the elevation of this is equal to 20 feet. And the only thing we don't know is what the pressure is, the dynamic pressure where it hits this. It's the same as the car going behind the jet engine and the jet engine hitting the car. Stagnation velocity equals 0, and therefore it pushes the car over because it translates that pressure into a force. So the net result of this is we have this expression here. So this is just what comes out of this. Whoops. Didn't need to draw a line through it. It's this. And so since we get rid of this 20 on both sides, it's just equal to this. And actually this is interesting because head is equal to pressure A over unit weight. Basically it's saying that this is no different than if you had a column of water that was sitting in a bucket and looking at the pressure here, this expression here, right? The same as the pressure in a static fluid. So it's interesting that the height of this column, because it's free falling, is just the same. Destroying that velocity is the same as just the column of water above it. It kind of makes sense. So what about so we have a pressure, and we know that pressure here, but we don't know what H is. So can we now calculate what that pressure is as a function of writing Bernoulli between point 1 and point A again? So we can do that here. What about point 1? We know the pressure at point 1 is equal to, well, we don't work in these mongrel units, but let's pretend we are for a moment, PSI. Again, big tank assumption. And elevation is equal to 8 feet. And so you write it between point 1, point 1, point 1, and point A. Again, we know that this stagnation velocity has to be 0 here. We know that ZA is equal to 20 feet. We know that the pressure A, we don't know, but we know it has to equal this. So I guess we know that this whole thing here is equal to H by definition. The elevation Z1, I guess, is 8 feet. This is 0, and this pressure here is 25 psi. And so, is there anything there that we need? I guess we have magnitudes, I guess, for all of these terms, and since this is now this pressure here, the only term in this equation we don't know is a value of H. And we can solve for a value of H, which turns out to be 45.7 feet. So that's it. So all we're doing is we're writing things in terms of the pressure here. The pressure here turns out to be just the pressure due to the column of water. Just turns out that way. We haven't made that assumption, but it turns out that way from Bernoulli. So we know that the pressure at this point, the stagnation pressure, has to be equal to H. So if we can now write it in terms of this expression here, because this system is completely defined, this really has everything defined to calculate pressure at A, we're able to calculate the height. So, yeah, all right, okay. We've used this, actually we haven't used this already. We haven't needed to use it, but we've made the point that we can use it. So we've said that if we only know 4 of the components of Bernoulli, then we can arrange it so that we take 2 streamlines, where this is a top streamline given here, and a bottom streamline given here. And by definition, the fluid velocities across those streamlines have to be 0, because that's the definition of a streamline. And so that everything that comes in on the left-hand side of this here has to go out of the right-hand side, because it's steady state. The amount that comes in here has to displace the same amount that goes out here. So we can write just an expression for the flow rate, actually a mass flow rate in this particular case. So mass flow rate at location 1 has to equal to the mass flow rate at location 2. So area times velocity is just Q. Amount multiplied by time is a volume. A volume times a density is a mass. And so this is mass in equals mass out. Usually the density coming in is taken as the same as the density going out, in which case these flow rates in and flow rates out are just taken as being the same. And so the reason for doing that is that in some cases we might want to not assume the so-called big tank assumption. And so this is a question here that involves the same deal. So we have a tank now which is being replenished by some flow rate from above, and that flow rate is just enough to keep the level of the tank constant. And so if the level of the tank is constant, then Q in has to equal Q out by definition, just in terms of words. And we already know if we would, for instance, write Bernoulli's equation between these 2 points, we know roughly that V2 should be equal to 2GH square root. And we get this by using the big tank assumption that V1 is not moving, it's zero velocity. And if we do that, we get a flow rate out of here, which we can calculate just from the height of this and gravity, nothing else. So this expression requires that V1 is equal to 0. But what if V1 is not equal to 0? V1 not being equal to 0 means that if we didn't keep on flowing water in here, then the level of this would actually drop over time so that it got lower and lower. And so what we can do is we can go back to Bernoulli and not make the assumption. So let's not make the assumption that V1 is 0. So we take Bernoulli. This is Bernoulli. What do we know at the top? At point 1, atmospheric pressure, 0. Elevation, h. But we're not going to make the assumption that V1 is 0. So we have pressure is 0. We have elevation is going to be equal to h. But we're not going to make this assumption that this is equal to 0. Downstream, atmospheric pressure, elevation equals 0, and an unknown velocity. And so we know each of these two terms, but we have two terms that are now linked and not removed. And we have one other driving term. So we have two velocities and one length. And so what we're interested in doing now is constraining this, because now when we manipulate Bernoulli, we have two velocities and we'd like to get rid of one of them. So we can write A1 V1 is equal to A2 V2. Right? So this velocity here, we know the diameter of this, so A1 is equal to pi d1 squared over 4, which is equal to pi lowercase d squared over 4 V2. Get rid of the pi's, get rid of the 4's, and so we have V1 is equal to the pipe diameter squared, the top of the tank diameter squared, times V2. This is just a constant, right? And so what we could do is we could now substitute this term into here. Well, we could square it. And substitute in here. And now this whole term is written in terms of the velocity coming out of the pipe and the velocity coming out of the pipe and a geometric factor. And all it does is it gives us now a velocity which is now modulated slightly to account for that. And so with this, this is now the new velocity. It's affected by the size of the tank. I suppose if the tank D goes to infinity, right? In other words, if the tank is really very big, D has to be very big. And if that's the case, then this term goes to 0, and then this truly is equal to 2gh square root. But if the tank is not infinity, but is much smaller, I suppose in the limits, I can't really get there, but if the diameter of the tank was equal to the diameter of the pipe, then all of a sudden this expression would actually blow up. But if the tank was not much, say 10 times larger than the pipe, then this would be a tenth, this would be 10 to the 4, then actually it would be a significant term. And so what you can do is you can calculate the flow rate that comes out of here as a function of this being an infinitely large tank, and you can also calculate the magnitude of the flow rate that comes out of this if it's a tank that's not infinitely large, and that's what this expression is here. It's saying that if the tank diameter is really, really big, then this expression here is basically 0, and the amount of fluid coming out of the tank is basically the amount that's calculated from 2gh. So the flow rate coming out of the tank Q0 is just equal to pi d squared upon 4 times V2, right? This is just the area times V2. And so we can calculate that, and that would be exactly the right answer. But as the tank gets progressively smaller and smaller, then the error that's enlisted in this comes about 5% after the ratio d over d is about 0.5. And so you can calculate what that magnitude would be. I guess the ratio of this as being 0.5 is that it's equal to the diameter of the tank is double the diameter of the pipe. And so you can imagine that for any reasonable size of tank, this is probably not going to be a bad assumption at all. I guess it's telling that. Okay. I won't do this last one because we'll do that soon enough and we're close enough to the end. We'll talk when we talk about balancing forces. So Bernoulli's equation just allows us to balance forces, F equals ma. We'll do the example of taking a gas cylinder in a lab and decapitating it and seeing how fast that gas cylinder travels. And we'll do something very similar when we do that.